you work out the units, this has units of, I believe, length. So let's wait. So this lambda is some kind of a length, and this is the healing length inside of a superconductor. And the physical meaning for this is precisely this distance over which the wave function is considerably different from a constant. So at the boundary, it must go to 0 because we're requiring it to be a hard wall boundary condition. And then the wave function heals itself, goes back to the constant value within this approximately this range of length. Okay. So that's the healing length. And this has some, this is a measurable thing too, and you can compare prediction in this experiment from using this. Okay, so anyways, we arrive at this equation. Okay. It's possible to derive the semi-empirical equations that governs the electrodynamics of the superconductor based on this equation, which are the Lambda equations. But we're not going to do that here. So now, let me move on to the real thing, which is this part will be more understandable to you. So far I have, other than Bose-Einstein condensation thing, everything else has been rather quantitative. Okay. So now let's do some real calculations. So we move on to the analysis of Josephson junctions. Okay. So now, what is a Josephson junction? A Josephson junction is we have two superconductors, and in the middle it's interfacing with maybe something else. It can be a normal metal, or it can be an insulator. And let's take it to be an insulator. So we have superconductor, insulator, superconductor. We have a junction formed like this. And what we have learned so far is that other than at the boundary, the wave functions inside of the superconductor are pretty much constant. And it's an overall wave function that models the behavior of every Cooper pair there. So let me call the wave function over here big psi 1. Wave function over here psi 2. Okay. Now, what's going to happen is now if we don't require the hard wall boundary condition at this insulator thing, okay, we're going to have, for the solution of that equation, we're going to have a decay outside. So it's not going to go strictly to the 0 now. Think about requiring this to be a finite variable instead of an infinite variable. Okay, so it's going to extend. And once this wave function extends over here, we have a similar scenario with, remember what we talked about in the tight binding model. You have two quantum wells, and the two ground states, due to their extent into the barrier, can talk to each other. And when they can talk to each other, they will mix, and the mixing will lower the energy. Now the wave function has physical interpretation. Now the wave function is actually related to the number of particles, the number of Cooper pairs. So we can say that if there's sharing of Cooper pairs across this boundary, there will be a saving of energy, and that's what's going to happen. Okay. So just think about the tight binding model we talked about before. So now, let's put a voltage across this junction. When we put a voltage across this junction, we connect it to an external circuit that looks like this. This is a plus terminal, minus terminal. We make a voltage appear across this. Okay. This is connected to the first part of the superconductor. This is the bottom layer. Okay, so maybe this is side, this is 2, this is 1. Okay, and now because we say that over here, the particles and the tunnel across is this barrier. So now let me call the phase of the two superconductors, chi2 and chi1. Okay, and we're going to study the relation of the phase and the number of particles across this junction. So for doing that, let's just use a simple time binding model kind of thing. But because of this bias, we no longer have a degenerate case. The two sides of the time binding model is no longer at the same energy level. We have something like this. Right? So now we should think, okay, if I apply a voltage like this, for the electron, which side has higher energy for the electron? This side, right? The minus side has higher energy for the electron. Okay. So we're going to say that, well, this is the well number 1, this is well number 2. Okay. And the voltage difference established is 2 eV. Something like that. Yeah, anyways, it's just EV. Okay. The separation. Okay, so let me reference the zero of energy being the midpoint of the energy of these two wells. Okay. Then I can write down the Hamiltonian in a 2x2 matrix form, which you have seen before. Okay. So this is going to be EV minus EV. Okay. So now I'm going to write the off-diagonal elements, which model the coupling between the two across the junction. Now we know that since this is non-degenerate now, according to non-degenerate perturbation theory, now how do we calculate the first order correction to the energy? We take the expectation value with respect to what? Yeah, of this off-diagonal element, right? And we know that mixing lowers the energy, right? So this matrix element must be negative. Right? So let's write minus k and minus k here. Okay. Now let's write down the component wave function. Okay. So let's think about expanding this. So across if I look across the junction, I'm going to see an overall wave function of psi. Okay. And it's not labeled by one. So let me now expand psi. Okay. In terms of the ground state wave function here and the ground state wave function here. But I'll put the information of the number and the phase to the expansion coefficients. So let me write that down. So I'm going to expand psi of is equal to sigma times, and sigma is a sum from 1 to 2. C times C of I 5, maybe I should use the ground state wave function in each of the wells. So what does this mean? It means that now this expansion coefficient carries not just probability kind of interpretation, it actually means the number of Cooper pairs on this side of the well and on that side of the well. And it also incorporates the phase information. So I'm talking about Ci of t is equal to square root of ni of t times e to the I of t. Okay? So now we write the Schrödinger equation in a kind of a spinor formalism, which we decompose it into a two-component wave function. And we turn it into a rate, sort of a rate equation of the time evolution of these expansion coefficients. Okay. So this is saying h times the expansion coefficients C1, C2, okay? This is equal to I h bar right. So now this equation we know how to calculate, right? Hopefully you know by now how to calculate this, if these are all given. And this is this EV is to convert voltage into energy for the electron, not the electron volt. Okay, you should understand that. Now let's just write down the two component equations and solve it. Are there any questions so far? No? Okay. So the first one is IH bar, and I'll start using this substrate notation for the derivative. Okay. C1 of t is equal to EV times C1 of t minus A times C2 of t, right? From that equation. Okay. This is the first line. So now I plug in this definition here of the number of particles, the particle density, and the phase. Okay, now maybe I should use a big N here, because we're not really considering the spatial distribution. We're just considering the number of particles is a function of time. So this is the total number of particles on this side, and the total number of Hooker pairs on this side. So now let's write that out. So this would be IH bar. And I'm not going to write the time dependence, but you should remember that number of particle and phase are all constants in time. This is the first term, and then you get an imaginary part, which is correct. This is equal to EV, writing everything out. Okay. So now let's work with this equation. I'm going to manipulate so that the chi1 is given to this factor here. Okay. And then I'm also going to, instead of divide by square root of n1, I'm going to multiply it through. So I get IH bar 1/2 plus I times E2 by 1 square root of n1. Remember we have, oh sorry, not square root of n1. We have multiplied through by square root of n1, so this turns into n1, this turns into n1, and this phase factor appears here, minus n2, n1, okay. Alright. Now we can correspondingly write down the equation for chi 2 and n2. Okay. So nothing changes except some sign. Minus EV C2 of t minus alpha C2 of t. Right? So now if we do the math, right, we can just rewrite this. Now switch the index and put a minus sign here. Okay. So that just gives you IH bar 1/2 and is chi1 minus chi2. So now we take this equation and we take this equation. Okay. And when we take the real part of this equation here, we're only going to pick out the time change of the numbers. Right? When we take the imaginary part, we're only going to pick out the time variation of the numbers. So it's 1/2 dt equal to EV over H bar. N1 minus square root of right? And then we can also write this for the second line, which gives us 2 minus now it's going to be sine of chi1 minus chi2. Well, let me turn that into chi2 minus chi1, which is adding a minus sign. Sine of chi2 minus. Okay. So now this is good. It says that if n1 and n2 were the same, right, then you see that actually the total number of particles is conserved. Okay. And then I can also take the real part and write down the time evolution of the two phases across the junction. So if I take the real part, I will get dt by 1 times n1. There should be see if I got this time.
How did you say you take the imaginary part of the equation to get the last two lines? Is that what you said?
Yeah, that's the imaginary part. Now
How did you pick up EV N1 on the right hand side? You take the imaginary part.
oh, yeah. Sorry. That's so they're just equal to the sign. Yeah. That. So for the real part, I have a sign. Maybe I have a sign error in my notes. Is this correct?
Take the real part?
Yeah, take the real part. I have I and I over here. It gives me a minus, right? And then, so the real part is just minus h bar dt pi 1. So that should be correct. I forgot h bar. Divide by h bar. Maybe I should divide by h bar here too. Yeah, I should divide by h bar here too. And then similarly for the other equation we have okay. So now we can do some cancellation in this one. Okay, so let me write. Okay, so first of all, there are a bunch of minus signs here, so I can turn everything here into plus signs. Okay. So now let me write the difference of the phase across the let me write chi2 minus chi1 is equal to 5. This is not the ground state wave function. This is the difference in phase across the junction. Okay, and I'm free to choose how. So maybe I can set this to be phi over 2, while this is minus phi over 2. Right? So their difference is 5. So let me plug that into here. I take the sum. Of the two equations. Okay. Yes. I take the sum of the two equations, and then so that I can cancel this term. Okay. So this one, if I plug in the chi1 equals to minus phi2, this is 1/2 dt phi, and 1 is, and then I plus this one, which is 1/2 dt phi and 2. Okay. On this side, clearly these two cancel. You have a combination of terms here, dv over h bar, n1 plus n2 here. So now you can go ahead and cancel n1 and n2. So you get the dt phi is equal to dv over h bar. All right. And then we put the voltage.
You need to say something, bro.
What is that?
You need to say N1 is very close to N2 before you can cancel that, or
No, I don't think so. I think particle conservation is here.
what is that?
But Feynman says you have to say that, but I don't think you need to.
You can cancel N1 and N2 on both sides.
Yeah.
What is the reason for that?
Because you can just combine them, right? N1 plus N2 here, N1 plus N2 here. The other term is cancelled. Feynman does a little bit of different thing. So he says, but I mean, I think his argument is also valid because the N1 and N2 are very, very large numbers, and at each time there's only a small current across the junction. So we can roughly say N1 is equal to N2. So we get this relation, okay, which will relate the time change of the phase across the junction to the voltage applied across the junction. Okay, so this is the first of the Josephson relations. Now let's work with this over here. Okay. So let me write the difference here, okay, which is so wait. Must be a minus sign. There's a minus sign here, right? Or here.
Here, oh.
But this one, right? Yeah. Okay. Because this one was chi1 minus chi2, and we switched the sign here. So now you say if I take the sum. Yeah, no, I was trying to say something else. So now if we take the sum of these two, we find that n1 plus n2 is that the time derivative of that is a conserved quantity. So that's good. Right? So we have particle conservation across the junction. Okay. So now let's just work with one of these equations. Let's say this one. Yeah, this one. So we said that the time derivative of the particles in well number 2 is equal to 2 times h bar half on square root of 1 and 2 times psi. In terms of the phase difference, we have to define sine of phi. Okay. Now the time rate of change of the particles in well number 2. Okay. This is the current flowing this way. Right? So if this loses particle, or if this gains particle, okay, right, because of the sign here, if this gains particle, if this side is positive, that means some particle, some Cooper pairs is flowing from superconductor 1 to superconductor 2 across the junction. Right? And that's a total current that flows which way? This way, right? Right? So when this side gains particles, we have a positive current. So now I can relate this to, I say that the supercurrent that appears across the junction is equal to some, and then now I'm going to be quantitative again, some critical current times the time of phi. Okay. This is the second Josephson relation. Now what is the critical current? Okay. I can't tell you that right now. It depends on this K factor. And it depends on the number density of the Cooper pairs across the junction. It depends on things that are not in our model. So empirically, if we do a measurement, we can find it. Okay. And there are also ways, very complicated ways to calculate this, which we will not go into. So these are the two Josephson relations. So our Josephson junction is some kind of a very interesting device. First of all, the current voltage relation is not linear. You have these two. Okay. So now let's see what we can get out of the Josephson junction relations. So now let's first consider the case where the two particles are degenerate, the two wells are degenerate, meaning I don't put any voltage across it. So when the voltage is 0, the phi is a constant, and it tells you that with 0 voltage drop, there is a current across the junction. Okay, depending on the initial condition of the phase difference across the junction. So when we say that with no current, with no voltage drop, you get a current, that's 0 resistance. Right? No resistance means it's still a superconductor. And so although you have a break in the superconducting material, because of this tunneling, this coupling across the junction, this superconducting insulator superconductor interface junction is actually still acting as a superconductor. Because you don't need any voltage drop, you get a current. Okay? And this is macroscopic tunneling effect. We have a bunch of Cooper pairs tunneling across the junction to give you that supercurrent. Okay? And that's based on their phase difference. Okay? Now let's think about what happens when there is an applied voltage difference. Okay? So now when there is an applied voltage difference, first of all, this equation is very simple. It's directly integrable. Let's think about a constant voltage. Okay. So I can write phi of t equals to the initial condition plus V over h bar Vp. Right. That's the case for a constant voltage across the junction. So now let me plug this into the Josephson current relation. So the supercurrent across the junction is given by IC times line of phi of over h bar. Okay, so we have, it looks like we have a sinusoidal current, and this phi naught doesn't really make any difference, just a phase. Okay, but if you think about the magnitude of things here, okay, what is E? This is 10 to the 6 minus 16. Right? Oh yeah, 19. And what is h bar? 10 to the minus 34. Right. So this is an extremely large number for small b. This is extremely large. Now, what this says is we have a current, we have a supercurrent that's extremely rapidly oscillating. So you have something like supercurrent as a function of p. This is like this. Okay. And you really don't get anything out of it. There's no DC component, and it averages to 0. So with a constant voltage drop, the phase is going to vary linearly, and you can stop the current altogether. You can stop a supercurrent across the junction. Okay. So with no voltage drop, there is a persistent supercurrent. But as soon as you add in a constant current, constant voltage, it becomes the current averages to 0. So that's quite interesting. This is called the ECE Josephson effect. Maybe we should stop here.
You can take 2 more minutes, I suppose.
Okay, 2 more.
Do you have anything else to say in 2 minutes?
Yeah, just the AC Josephson effect, I guess.
Yeah, you can mention that briefly.
All right. So let me mention that briefly. Now, when you add in a voltage, if you add in a time-dependent voltage, it turns out you can actually get a time average current to flow across the junction. Okay, And basically you add in a voltage that's of the form, you have a DC component, plus an AC component times, what is the sine of the sine omega t. And then let me just tell you that when omega matches the Josephson frequency, maybe we can talk about this at the beginning of the next lecture. Okay. When the, where is the Josephson frequency? So omega is equal to 2e over h bar v dot. Then you actually have a non-zero current. The current acquires a DC component, which is saying that, well, the current is still very rapidly varying because you have this DC component. But then it averages to here. Okay, and there's a current here.
What is this frequency?
This is the Josephson.
What range? Is it gigahertz or?
Oh, depends on your bias.
High frequency.
Depends on your bias. It will be pretty high frequency there. So this is a bias dependent frequency.
But it's very high.
It's very high. And also, actually, doing a more involved calculation, you'll find that there are a bunch of voltages, there are a bunch of frequencies where you can satisfy that the superconducting current averages to a remaining DC component. And in fact, what you can get is, you can get the IV characteristic looks something like this. Okay, so it approaches a linear thing because then it's non-conducting. And then these jumps in the current and in the voltage. This side is voltage. This side is the supercurrent. Okay. This jump in the voltage is actually given by E over H bar. Am I right? Sorry. The jump in the voltage is H bar omega over 2E, and omega would be your bias frequency, the frequency of the AC oscillator. And this is called the dual steps. Okay. So the Josephson junction has a bunch of interesting current voltage relations. And that's just one use for it. In the next lecture, perhaps we can talk about the actual Cooper pair box. And we can talk about that in the context of quantum computing. Because it's actually a very good candidate to do quantum computing.
Okay, you'll get 2 weeks break, and then we'll keep our take home exam this afternoon.